Here we are for activity 7. If you have not started on this activity yet, please go and try it yourself. And then when you get stuck, come back here. All right, so here's explanations for each one. 1A, can a 3 by 4 matrix have independent columns and independent rows? Okay, so 3 by 4 means that we've got 3 rows, 4 columns, maximum 3 pivots. And so if we were looking at the columns, we could have 3 columns that are pointing in different directions, but these column vectors are in R3, so there's really only 3 dimensions to work with. So can we have independent columns? No, because that 4th vector is a problem. So no, well, okay, let's just, instead of writing no independent, let's just write dependent columns. Okay. And then for the rows, yes, these vectors live in R4 since they have 4 components. And you can go 3 different directions in R4. So independent rows. No problem. So this is in R4. Whoops, that's not a very good exponent. In R4. And these are 4 vectors in R. Wow, 3. All right. All right, that's 1A. 1B, if we've got a 4 by 3 matrix and it's rank 2, can it have independent columns and independent rows? Well, it doesn't have full column rank or row rank. Not full column or row rank. So no. Yeah, that would only have 2 pivots. All right, why does the rank of A equal the rank of A transpose? Well, basically, either way you flip it, it's going to have the same number of pivots. Yeah, either way you flip. Whoops. Oh, jeez. I need to zoom in. Either way you flip, same, wow, number of pivots. There we go. Get a little bit more control. Can the null space of a 3 by 6 matrix have dimension 2? Actually, was this one on the video that I did last time? For maybe section 5.3-ish? Yeah. Can the null space have that dimension 2? So if we are working with a 3 by 6 matrix, that's 3 rows, 6 columns. Which means that we are undergoing a transformation that starts off in R6 and gets squished down into R3. Because the image of this transformation is the column space, and all of these columns are R3. Yeah, we know that, yeah, if we're multiplying taking a 3 by 6 matrix, we would have to multiply that by a 6 by 1 vector. And in the end, that would give us a 3 by 1 vector. as an answer. So yeah, this is a transformation from R6 onto R3, and therefore it is necessary to have at least 3 dimensions of squishiness. Yeah, necessary to have 3 dimensions of squishiness as a linear transformation. So, at least 3D null space. So the dimension of null space would be at least 3. Could be up to 6, depending on what the matrix actually was. Okay, moving on. Part E. Suppose that A is 5 by 4 and the null of A is equal to the span. Okay, so the null space of A is equal to the span of some column vector that's not equal to the 0 vector. Can the rank of A be 2? Oh, interesting. So we're saying with this condition that the null space of A is one-dimensional. So the dimension of the null space is 1 because it's spanned by one vector. Oh, and this notation's a little bit bad. This notation's a little bit bad. It shouldn't be a column. Scratch that. Equals the span of V for some vector that is in, R4. This is a transformation from 4-dimensional space onto 5-dimensional space. And so we need this vector to originate from R4. And the columns of the matrix A would actually be 5-dimensional. Okay, so I made a boo-boo there. I'm sorry. Yes, this vector needs to be 4-dimensional. But the question still stands. I mean, I think what I was trying to do when I made this question was say that the dimension of the null space is 1, and we're asking the question, can the rank of A be 2? Okay, so yeah. We are looking at a transformation that maps R4 onto R5, 4-dimensional space onto 5-dimensional space. And in order to have rank 2, if we were going to look at this, so 1, 2, 3, 4, 5, 1, 2, 3, 4. Okay, so there's our matrix. In order to have rank 2, we'd need 2 pivots. And so, in a reduced echelon form, everything down here, all of those would be zeros. And no, not that kind of R. I don't need the fancy R. R, R, E, F. And therefore, we would have 2 free variables two free variables, and that means two-dimensional null space. So yeah, so a rank of two means that we have a two-dimensional null space, and so these things can't coexist at the same time. The null space can't be one-dimensional and two-dimensional at the same time. Okay, and then part F. There's A. What's special about the column space and null space of A? Well, I could take a look at this matrix and look at the column space. The column space, whoa, is the span of all of the columns. And in this case, really the only column that's worth anything is 1, 0, which is, basically the y-axis. No, it's the x-axis. My bad. This is the x-axis. That entire line. And if we wanted to find the null space, we would take our matrix and we'd be solving for ax equals 0. We'd be solving the homogeneous system of equations. And so here's the augmented matrix. But yeah, again, what does that say? It just says that x2 would equal 0 here, and x1 is a free variable. And so that's written in the opposite order of what we would normally do. But that results in a parametric vector form that looks like t times the vector 1, 0, which again is basically the x-axis, right? And so the thing that's special about the column space and the null space here is that they're the same. This is a weird transformation, and I wonder what it would look like if I animated it. I think I've done that before. Let's see if I can find a 2D animation just to show you what it looks like. Uh-oh, some people chatted with me on Pronto. Oh man, let's crank this up. GeoGebra. Let's see. Open 2D transformation. Oh, come on. What? All right, let's go back here. Thought for sure it was called 2D transformation. Please, I want to look at mine. Getting all these other people's. Really? Transformations. All right, I'm striking out. But if you are at all interested in, taking a look at what that would be, nope, just kidding. What that would look like as a transformation for the column space and the null space to actually be the same thing. Essentially what you would imagine is you're taking two-dimensional space. All of the points along the x-axis are actually being shrunk to 0 at the same time as the entire space is kind of being flattened out onto the x-axis. So it's a little bit weird, but I would imagine that would look somewhat, I don't know, rotatey as it happened. Okay, anyways, number 2. Here's a matrix in its reduced echelon form. Since we already have the reduced echelon form, this won't be too bad. We just need to find a basis for the column space and the null space. So we have 2 pivots. That means that, yeah, we can pick these 2 vectors as the basis for our column space. So, yeah, the column space is the span of 4, 6, 3 and 5, 5, 4. Cool. Yeah, there are only 2 pivots here, so we're only able to cover basically a plane in the column space. And then the null space, let's do that in blue. The null space, imagine that we were solving the homogeneous system AX equals 0. All that would change here is that there would be a 0 vector on the end. So what we have for the null space is 2 free variables. And we'd have, a set of equations that look like x1 equals, I'm going to subtract over the other pieces. So I'm looking at the, first row here. But x1 would be 4x3 minus 7x4. x2 would equal negative 5x3 plus 6x4. And then x3 would be a parameter and x4 would be a parameter. I don't know, you could call them T and S. You could keep calling them x3 and x4 if you want. But in either case, that results in a parametric vector form where we have, t is the same thing as x3, so we've got 4, negative 5, 1, 0, corresponding to t, or negative 7, 6, 0, 1 for the one that corresponds with S. So this one's for t and this one's for S. But it would be the span of those 2 vectors that would give us the null space. Yeah, and the null space should be 4-dimensional overall. We would have the general form of AX equals B, where A is 3 by 4, X is 4 by 1, and B is 3 by 1. And, the null space lives here. Nope, shoot, I used the wrong color. The null space lives here in 4-dimensional space. It's all of the vectors that get squashed onto the 0 vector, just like in this equation. And the column space are all of these vectors B that we're able to reach. And we're able to reach basically a plane in that 3-dimensional space that's spanned by the 2 vectors that we found. So 2-dimensional in each case, but one lives in R3 and the other lives in R4. Okay? And our last one. Here we have been given, well, at least a spanning set for a subspace S. Hopefully these things are linearly independent. It looks like they are. Oh, yeah. So if we subtract, okay, let's say we could subtract real quick. Here, let's call these x1, x2, and x3 as vectors. I think that'll match the notation that was used in the book. If we took x2 minus x1, we would have the vector 4. Oh, I thought this was going to be better. -2 and then 0. There would be other ways to combine them. Anyways, that was anticlimactic. I wanted to show that, yes, these would all be independent. I'm pretty sure that they are. We're being asked to find an orthonormal basis for the subspace. So, I guess it's kind of foolish for me to assume this, but I'll find out. I'll find out along the way if these are not linearly independent. We'll find that through projections. Okay, so first off, we will let our first orthogonal vector be x1, and now we're using the Gram-Schmidt orthogonalization process. We're letting our first orthogonal vector just start off with x1, and then for our next one, we'll take x2 and we'll subtract off x2's projection onto f1. And that'll look like, well, let's actually just write this vector out so we can start doing some math. 5, 0, 1. This is the dot product between x2 and f1 on top. So 5 plus 0 plus 1, so 6 on top. And then this is the dot product of f1 with itself. 1, 4, so that's 5 together, and then another one, so 6 on bottom. So we're going to subtract off one of these and get 5, 0, 1 minus 1, 2, 1. Whoops. And that's 4, -2, 2. All right. And then for F3, I guess we could do just a quick check to make sure that the first two vectors are actually orthogonal. We could take the dot product of 1, 2, 1 and 4, -2, 2. And we get 4 on the top, and then we'd get -4 here, and then 2 there. That doesn't seem right. Because I didn't subtract. Good grief. Thank you for already catching that, to those of you who already did. I'm an idiot. Okay. Now we've got 4 and -4, so we're square. This dot product is 0. Cool. And then the next one, we would take our third vector and subtract off its projection onto the first orthogonal vector and its projection onto the second orthogonal vector. So 4, 3, 2 minus its projection onto yeah, f1. So let's take the dot product of x3 and f1. So 4 plus 6 plus 2 is 12. And we're going to divide that by 6, which is, the length of x1 squared. And we're going to multiply that times 1, 2, 1. And then we're going to subtract off the projection here, taking the dot product between x3 and f2. So, first components here would be 4, so that would be 16, and then we would subtract off 6, so that gives us 10 on top. And then the length of f2 squared would be 14 plus 4, 16 plus 4 is 20. Ooh, nice. It's almost like somebody cooked these numbers so that they'd work out nicely. Okay. 4, 3, 2. Minus 2 times this vector. So let's go -2, -4, -2. And then 1/2 times this vector. Shoot. I didn't need to do the negative part on that last one because we left the minus sign there. 1/2, 2, 3/2, and 1. Okay. So 4 times 2, or 4 minus 2 is 0. 3 minus 4 minus 3/2, good grief. 3/2, what are you doing to me? 2.5 minus 2.5. And 2 minus 2 minus 1, so it's -1. All right. So now we have our orthogonal basis. Orthogonal basis. Where we've got 1, 2, 1. 4, -2, 0. And 0, -2.51. To make these into an orthonormal basis, we have to normalize all of these. So I'm going to say f1 becomes, let's call it u1 for unit vector. And then we'd have to divide by the magnitude. In this case, the magnitude was the square root of 6, right? So, basically this would be 1, 2, 1 divided by the square root of 6. U2 would be that same vector, 4, -2, 0, and we'd have to divide it by, what did we say, 20? 20. So the square root of 20. And then U3 would be 0, -2.5, and 1. Don't make me do that. So that's 6.25 as a squared. So it's times the square root of 7.25. Great. So all of those could be unit vectors. Feel free to check me on that. I might have made a mistake. Another great thing to do would be to actually graph what's going on. Use GeoGebra to plot these in 3 dimensions. So start off with your original 3 vectors, x1 through x3, and then visualize what happens during the Gram-Schmidt process and all the new vectors that you get, and you can plot them all there and just make sure that everything is the way that I just said it was. But I think that'll take me too long to do on the iPad. So I'm going to end the activity video here, and I will see you in the next one, or hopefully see you in pronto. All right, bye guys.